Thank you for coming, and thank you for inviting. Thank you to the organizers. Liz and I actually go back like 10 or 12 years or something like that. Although we haven't seen each other in a while, but we overlapped a little bit at Purdue, so that's how we know each other. So I'm going to talk a little bit about the Collatz conjecture. I'm going to give you guys this function, this conjecture defined over the natural numbers, and then I'm going to, with some interesting results about this problem, and then I'm going to look at what we did, some of the results that we got from this RU that we did, where we looked at this function over the Gaussian integers. But let me start off just saying a little bit where I'm from. So my mom is from this little town outside of Guadalajara down here, and my dad is Tex-Mex from somewhere near Austin, maybe like an hour from Austin. And I grew up in the Bay Area. Actually, I was at a talk earlier today. I went to San Jose State University, and I saw that somebody else here, at least there's one other person here that's from San Jose State. So that was really nice to see. And I went to Arizona for grad school. Actually, before that, I spent a minute at University of North Dakota over here, and then at Purdue with Liz, and I've been at Eastern Illinois University since 2013. But for 3 years, 2018, 19, and 20, I took a leave of absence, and I spent those 3 years working for the Navy in Panama City, Florida. So what I really enjoyed about that was I got a little bit of both worlds. I always wanted to know, what is it like to work in government or industry? What's it like to work in academia? And so this was a really nice visit. At the end of those 3 years, I did have to decide, what am I going to do? What do I want to do? What's best for me? And at that moment that I made the decision, the best decision for me was to return back to Eastern. And so that's where I've been since January 2021. Okay, so I made a comment earlier that the talk today stems from this REU that I was a mentor for. So this was from 2017 at CSU Channel Islands. So this is in California, just north of LA. There were 4 projects, 4 faculty mentors, and these are the 4 of us here on the left. And on the right, these were my students, Eric, Rafael, and Jason. So Eric is in Boulder, Rafael is at Purdue, and Jason is in Wisconsin, and he should be graduating, or maybe he just graduated. He's going off to Sandia, I think Sandia, I wrote this down, Sandia National Labs this fall. And Eric and Rafael, I think, have 1 more year. Okay, so the results I'm going to be talking about today stems from the work that really they did. So, okay, if you're going to give a talk on the Collatz, you usually want to throw in this picture. It's also known as the 3x plus 1 problem, and you can see why that is from here. So it says, this is one of those XKCD comics. It says, the Collatz conjecture states that if you pick a number, and if it's even, divide it by 2, and if it's odd, multiply it by 3 and add 1, or sometimes you divide by 2 just to kind of make the trajectories go a little faster. And you repeat until eventually your friends will stop calling to see if you want to hang out. So, but either way, it's a fun problem. It's an interesting problem. There's even a whole book dedicated to this. I think what Ligarius had done was originally, I think he had a whole website dedicated to it, and then I think he made it into this book. But this is a really nice book, just full of resources, full of different references and what sort of works and modifications of this problem that they have done. So it's a really nice book. Okay, so this 3x plus 1 problem also can be, this Collatz problem is also known as the 3x plus 1 problem. And it's named after this German mathematician who was interested in the behavior of recursive iterations of functions over the positive integers. He was interested in their graphical representation. So it seems like this problem may have circulated orally at this conference. What is this? The International Congress of Mathematicians in around 1950, but it didn't appear in print until 1971 by this written lecture by Coxeter. Okay, and this is just on the left here. This came from Ligarius's website, where this is just some hand sketching that Collatz had done, and I thought, well, this might be interesting to throw in there. But really, there's just a wealth of information on this particular conjecture. All right, so let me give you guys the function a little bit more formally here. So it goes as follows. So again, if it's odd, or in other words, if 2 does not divide x, we're going to take 3x plus 1. Otherwise, if 2 divides x, we're going to divide it by 2. And the conjecture states that the trajectory, or you may also hear the term hailstone sequence, the trajectory of n will eventually reach 1 for every positive integer n. And maybe I should have used x here, so sorry if I confuse you there. So the first time I gave this talk, it had been shown by brute force up to about 2 to the 60. And the most recent time that I checked, it's now been checked all the way up to 2 to the 68. So it's been shown to hold that you start with any integer, positive integer, up to about 2 to the 68, and eventually that will come back to 1. And in Quantum magazine, I think both of these statements come from that magazine, Tao has said that almost all the orbits, all the trajectories attain almost bounded values. And Ligarius is quoted as saying that this is a really dangerous problem. People become obsessed with it, and it really is impossible. So as stated, this is about as far as we've gotten. But there's also been variations of this problem, right? So maybe instead of 3, pick some other prime number, or instead of 2, pick something else. Or maybe instead of looking at the Collatz problem over the integers, maybe look at it over some other lattice, which is what we had done. So more Collatz. If you Google the Collatz problem or the 3x plus 1 problem, you're going to find all kinds of information. So in particular, there's a website for this Millennium Prize. There's these 7 unsolved big math problems where if you solve them, you can earn $1 million, right? For the Collatz Prize or the Collatz Conjecture, there's a Japanese company that posted here. So they're responsible for mathprize.net. They have a prize of 120 million yen, and the last time I checked, that's about 862,000 US dollars. So there's this, these other 7 math problems, but similarly, there's this other one for the Collatz problem. If you can solve this, you win this much money. There's also a YouTube, what do you call it? YouTube link or YouTube website where called Numberphile. I don't know if you guys have heard of it. So there's lots of videos there. There's 2 on the Collatz. There's one that's a little older, and then the more recent one. I think it might be this guy Brady here that talks about it, and he kind of talks about it in a little different way and imagines it a little differently, where they look at the Collatz problem, but visualize it more as something that looks like a seaweed. So there's different ways you can think about this problem, and this one was just interesting. And if you look at the second video on the Collatz conjecture, when you look at the drawing that they make, it's actually really nice. It's really interesting. And if you wanted this picture, you could get it from their website, or you can purchase this coloring book. where there's lots of other visualizations. I don't know what's in there, but this one was really interesting. Just another way to look at the Collatz problem. And you'll see again, you'll see in a moment kind of where this comes from. You want to play around with some numbers. There's also this Collatz calculator right over here. Okay, let me see. All right, so why do people think, or those that have studied it, why do they think that any trajectory will eventually reach 1? There's this paper by Crandall from 1978 that presents heuristic probabilistic arguments. If you've taken a probability class, you can kind of follow along and see what he's saying there. But he basically constructs this PDF. And so we have this discrete PDF and calculates an expected value. And from Ligarius, where did this come? I think this was from Ligarius's website or his book. But he summarizes it by saying, if we consider only the odd numbers generated by the Collatz process, then each odd number is on average 3/4 of the previous one. So this yields this argument that every hailstone sequence should decrease in the long run. Right, so in other words, if you start with an odd number, apply the Collatz function, okay, and it's either going to be even or odd. And so half the time you expect half the time to be even, half the time to be odd. If it's odd, you stop. Otherwise, if it's even, apply the Collatz problem again. And half the time it's even, half the time you expect it to be odd, and so on and so on. So that's basically what they're doing there. So the next few slides, I'm just going to show you some visuals. I had shown you already this seaweed visual, and you could think of basically right in here where that 1 is, that was the starting point of that seaweed. And then here's the rest. So, and you can see that, say, for example, 21 is odd, multiply it by 3 and add 1, you get 64. But also 128 is even, divide that by 2, you get 64, and so on, and you get this visual. So this is kind of just zoomed in for those 10 steps or less. If we zoom out, we get something like this. And if I remember correctly, this one on the left was the one that my students drew, and I think this one's on the Wikipedia page. So that one's coming from the Wikipedia page there. More visualization. So the image on the left, so for example, if we started at 27, it takes 111 steps. So we apply this function, or we compose this function 111 times. And then we eventually, after 111 times, we get back to 1. And the maximum value that we reach in that case is this 9,232. The image on the right represents, so our x values here, think of all these as different starting values, say from 0 all the way to 2,000. The height represents the highest number reached. So say, for example, x is 27, that's somewhere down here. The max that it took was this 9,000. So that's maybe somewhere around here, close to 10,000. And you can kind of see that it looks like something interesting is happening. There's some interesting visuals here. And so it kind of makes you wonder, well, maybe if x looks like this certain type of integer, then what sort of properties does it have? So there's lots of different things you can do or think about with this problem. Oh, whoops. All right, so I made a comment earlier about, all right, so we have this Collatz problem. We think about it over the natural numbers, basically, but we can also generalize. So there's two things we can do. Maybe we could generalize it. Maybe instead of mod 2, take it mod something else, maybe mod 10 or mod 9 or something. Instead of 3x plus 1, what if it's, I don't know, 5x minus 1, that sort of thing. So we can think of it still over z, but in a more general form. We can also think of this problem, which is one of the things that we did, was maybe over other rings. So instead of the integers, what about the Gaussian integers? Or what about the Eisenstein integers? Or maybe some other rings? Well, there's this really nice paper from 2016 in which this author considers the Collatz mappings over free abelian groups of finite rank. Here's an example of what he looked at, which was originally studied in this other paper. And whatever Kionki did in his paper, right, so instead of z, replace that with z squared of 2. So these would be integers of the form a plus b squared of 2, where a and b are both rational integers. And what he was able to show was that indeed there does exist divergent trajectories. So in that case, if we replace z with z squared of 2 and maybe modify this Collatz function a little bit, we will get divergent trajectories. So a little bit of motivation. I'm kind of looking at something a little differently here, because this is kind of what motivated me to want to even look at what's happening over the Gaussian integers. The year prior this REU, I was working with a student, and we looked at, we were reading this paper by Gethner, I think I'm saying it right, Gethner, Wagon, and Waite, called A Stroll Through the Gaussian Primes. And the question was, in that case, is it possible to walk to infinity using the Gaussian primes, and I still need to define Gaussian here, the Gaussian primes as stepping stones and taking steps of bounded length, right? So imagine you trying to jump on these steps, and there's only so far you can jump. And if we try to ask the same question, but instead over the real numbers, we cannot walk to infinity on the real number line. We can take steps of length n for any n. So if you look at each one of these numbers, right? So this is composite, it has a factor of 2. This has a factor of 3. None of these are prime. None of these are prime here, for example. And then if we ask the same question over the Gaussian primes, and those Gaussian primes are these black dots here in this lattice. If we pick a distance, how far can we go? You can kind of draw this pattern here of how far can you go? How far can you step? So this was a motivating question to even think, for me to even think about what's happening over the Gaussian integers. But okay, before I even, you kind of have an idea of what I mean by Gaussian integers here on the left, but let me define this more formally in just a moment. But let's think back to just the integers. Just the integers. What do we know? So if we're just talking about integers, rational integers, we can ask, here's a number. Is it prime? Is it composite? Is it even? Is it odd? We can ask whether it's a unit, whether it has a multiplicative inverse. We can take its absolute value, maybe even apply the division algorithm. We also know that we can factor a number uniquely up to associates. And we can order, right? Especially, so in particular, if we were just looking at the natural numbers, we can order this, right? 1 is less than 2, 2 is less than 3, and so on. We can put things in order. But now if we're looking at a lattice, that's, how do we order? How do we say this number is less than this one? Or what's the equivalent way to say something like that? Okay, so the Gaussian integers are numbers of the form a plus bi, where a and b are rational integers, and I is this imaginary number, this complex number, where I squared is -1. And we have some properties, and I'm not including every single bit of detail here, but if we have a rational number that's congruent to 3 mod 4, then that number is going to be prime. If it's congruent to 1, then we can actually factor it, and each one of these, a plus or minus bi, is going to be prime. Previously, I made a comment about absolute values. We can do the same thing here, which would just be the square root of the norm here. A squared, the square root of a squared plus b squared would be the absolute value. We can talk about units, just like we did with integers. We can talk about units here, but now we actually have two more, not just plus or minus 1, but plus or minus I. And we can talk about having numbers that can factor uniquely as a product of primes, right? So for example, 2 can be written in these two different ways, but really they're the same. Really they're the same. And finally, here's what we really wanted. Here's what I really wanted, was a way to construct an ordering of the Gaussian integers. And this idea came from contacting, so that's I think early that summer, once we kind of knew what direction we wanted to go in, I had contacted somebody who had some material, and they had done an RU that included the Gaussian integers, and I messaged them. And they had suggested, they had this paper where they had this spiral ordering of the Gaussian primes that kind of follows a similar pattern to the rational integers, where you have even, odd, you have some of these primes along the way. And if we restrict ourselves to that first quadrant, then we can talk about, we can basically do this ordering, what they call the spiral ordering. So these folks did something with, this paper has something about, includes this image, and they somehow use this in their work. And when we were emailing, one of them had suggested that they had considered thinking about the Gaussian, or they had considered looking at the Collatz problem over the Gaussian integers, but they had never, either they didn't have time or maybe their students weren't interested, so we ran with it. And here's what it looks like. Okay. All right, so over the Gaussian integers, if I start, let's just say I start off with the value in the first quadrant here. I can define this new Collatz problem as follows. 2 plus I times some number, right, some Gaussian integer plus a unit. If, so we do this if 1 plus I does not divide z, or in other words, we'll just say z is odd, and if it's even, or if 1 plus I divides z, we're going to take z and divide it by 1 plus I. So this looks like it's going to behave the same, or at least very similar, right? If it's even, do this. If it's odd, do that. And here's an image that my students generated. And again, you can kind of see that there's a similarity where we have, it looks like it's approaching 1, or a unit, I should say. And then we have all of these branches here that approach this number. Okay. All right, so a couple other examples here, a few more images. So this image on the left here, okay, so we looked at the trajectory of these two different Gaussian integers, and I'm using the unit u as 1 here in this case, right? So my unit here, I'm just picking 1 for now, for this example. And on the left-hand side, we started with, okay, so I think I started with 10 minus 2i. And after, so it did not return to its unit, any unit, after 10,000 steps. And only the first 50 steps here are shown. Now, so the height, the y values here, represents not the integer itself, but the norm of that integer. It's either, yeah, the norm of this integer. So we can see that even after 50 steps here, it looks like it's still increasing. It doesn't, it's not, I mean, and within 10,000 steps, it didn't return back to any unit. Whereas this one here, here's an example where it does. So we definitely know there's examples where of Gaussian integers where it does return to a unit, and examples where so far it hasn't, up to at least this value. I don't know if anybody has checked values greater than that. So you're welcome to this. You're welcome to try that. Just some interesting phenomena that my students found, and this is just a few. There were many more interesting observations. These are just a few that I'm listing here. So they looked at, for example, plus or minus 100 all the way to plus or minus 100i. They found that about 5% of the Gaussian integers landed within 10,000 steps. The slowest, or if you want to say the longest trajectory, took 251 steps, a tie between these two numbers. So there was something interesting here because these two were right next to each other. So we're trying to figure out, there wasn't enough time. I think we only had 6 or 8 weeks. There wasn't enough time to figure out, but there were a lot of cases where these two numbers that were next to each other took the same number of steps. No Gaussian integer tested took between 252 and 10,000. And there were several instances of neighboring Gaussian integers landing in the same number of steps. So that was basically what I had said earlier. And then if we try to follow Crandall's argument for the Collatz function, then in that case, we expect the behavior of the trajectories to increase without bound. Yes? Go ahead.
What do you mean by 5.6% kind of density? Are you using like critical density or?
So basically 5% of all of, let me see.
It's not well defined unless you take like capital density or some other kind of.
So I'm trying to remember. So out of 23,730 values, about 5% of those.
Those ones.
Yes.
Okay.
Yeah. So what were you thinking? Go ahead.
Just out of those guys, not out of all of Gaussian.
No. Oh my gosh! If we could have done that.
I thought you had. Okay.
No. This was only for the ones that we looked at, only for these ones here. Because at some point, for a lot of these, right, so we only rounded up to so we didn't have, let's see, I'm trying to think back. We just didn't have enough time to run these computers long enough, or whatever work that they were doing. They had written some programs or some functions in Mathematica. That's what we were using at the time. And we just didn't have the resources to let it run and run and run. So that's something that could definitely be improved on here. But no, thank you for asking. Please, if anybody else, yes.
Is that also where the 23,000 number comes from? Did you not get to all 40,000?
Yeah, we just didn't get to all of them. It's arbitrary. Yeah. We just didn't get, we couldn't test as many as we wanted to. This image here, this is just a visual just to kind of show you. In one case, we used a unit of 1. In the other case, we used the unit of -1 in our Collatz function. And we highlighted these just to kind of show the pattern here. So if something happened here, we just did this line, and over here, if these numbers came up, just to highlight that, hey, we got some symmetry here. We got some symmetry going on. So why we have 4 units, but we don't really have to look at 4 functions with these 4 different units. This is enough to say we really only need to look at this Collatz function just pick one of these units, just say u is 1, and then we just expect that for any other of the units that we use, something very similar is going to happen. And that's where they came with, so they called it the TKC proposition. I guess that's a thing, because earlier today at a talk that I was at, there was this Merck theorem. And I guess RU students like to write their theorem or proposition or whatever results using their initials, is what it seems like. So that's what they called this here. The TKC, let's see, was that their first? That was, yeah, that was for their last name. Merck, I don't remember if that was for your first names or last names, but whatever, it doesn't matter. So they came up, they saw these interesting results, and they came up with this proposition that a Gaussian integer lands using this unit, call it U1, if and only if its associate lands, if the associate is U2Z, lands using the unit U1, U2. So this was just some interesting results that they found, and I've listed some examples here. Okay, so something else here that was interesting. We say that we call an odd Gaussian integer a primary odd integer if it maps to a power of 1 plus I. And part of the reason why I throw this in here is because of something interesting that was found. So let me see. So the students wrote it in this form, or you could write it recursively in this form, but you could also write it what they call the scary form. And what was interesting in the scary form is that the ace of I's here, we looked at the sequence of ace of I's, and I remember thinking, oh, I wonder if this is a sequence that can be found in the online encyclopedia of integer sequences, and sure enough, it was there. And if you type this in, I don't remember where else this comes from, but we found it here, but it was also in other areas of mathematics. So I just thought this was really, really interesting. You never know. You never know what you're going to find. Coalescing points or merging points. So these were when the cases where we had two numbers, for example, an even and an odd number, and it mapped to the same number. That's what we call a coalescing point. And you can show, so I'm jumping back to the original Collatz over Z or over N. It can be shown that a coalescing point, I'm sorry, no, never mind. I'm talking about Gaussian here. Z equal to A plus BI must be even, and A must be congruent to 2B plus 1 mod 5. So this is just something else that they did for looking at the Collatz over the Gaussian integers is what are some of these properties? What do these coalescing points look like? And those particular pairs of A, B satisfy these congruences. Remember, we're taking these mod 5. And so really, if you look at Z5 cross Z5, there's these 25 possible values, but they only satisfy these last congruences, these 5 values here of A, B. And you can actually show, let me see. So if Z is a Gaussian integer, and if we consider the sequence or the cycle of pre-images, you can show that these cycles, they partition Z5 cross Z5. And you end up with these 3 subsets of different sizes. And these elements here fall into 3 of those 8 subsets. Oh, whoops. Let's see. Okay, so for the sake of time, I'm going to skip this here, but this was just something else that they found. They found this binary interpretation of the integers, both in Z and over Z of I. Just something interesting to note here. Okay, so I want to now say a little something about Eisenstein integers. So once we looked at the Collatz conjecture over the Gaussian integers, I thought, well, what about if we look at this over the Eisenstein integers? This was part of the motivation. The reason I was thinking about Eisenstein is because I had done this work with one of my students, in which she also had, right, so remember there's that paper where they look at the Gaussian primes, the Gaussian mote problem. And so then her and I looked at the Eisenstein mote problem, right? And so these look a little similar to the previous two for the Gaussian. And so because I was already thinking about the Eisenstein integers, I thought, well, maybe we can think about the Collatz problem over the Eisenstein integers. Can we come up with a Collatz-type function where instead of z or z of I, maybe z of omega, where omega is this special complex number? But okay, so let me first say, what are these Eisenstein integers? I kind of already gave you a visual. Okay, it's basically this lattice in the complex plane, and those black dots here are these Eisenstein integers. So for example, 2 here, this is so think of this x-axis as the integers here. So 2 is a rational prime, and it's also an Eisenstein prime. 3 is not prime here, but 5 is. Okay. All right, so the Eisenstein integers are integers of the form a plus b omega, where omega squared plus omega plus 1 is 0. And it forms instead now this triangular lattice. We can talk about the norm again, and the norm looks like this. We can talk about Eisenstein primes. And again, I'm being a little bit hand-wavy here. I am kind of missing a little bit of details, but if we have a rational prime p congruent to 2 mod 3, then p or p omega are going to be Eisenstein primes. And again, we can factor these or write these as a product of primes up to associate. So it holds a lot of those same properties that it did for the rational values, the integers and the Gaussian integers. So before we finished up our REU, one thing we tried to do was come up with this spiral ordering. And we didn't get anywhere. We tried, so again, this is another problem that I know of, is can you come up with some sort of spiral ordering, kind of like the way we did for the Gaussian, where it alternates parity, right? What we called even and odd. Can we do something similar? So we didn't, like I said, we didn't get very far with trying to come up with a spiral ordering, looking at, say, what's happening in this quadrant here. But they did at least come up with a Collatz-type function, but instead of 2 congruence classes, in this case, we have 3. And this is what it would look like. There has been some work, right? I made this comment earlier. There has been some work of looking at the Collatz mapping over the ring of integers of some other algebraic number field, not just the Gaussian or the Eisenstein. But in terms of the Eisenstein integers, this is what it would look like. And if we again follow Crandall's argument, it looks like in this case, so this is just a conjecture here, that from the experimental results that they did, that it looks like the Eisenstein integers will eventually reach 1 in this case. Or if we look at a Collatz-type function over the Eisenstein integers. Okay, and just as an example, here's what that looks like for the first few. And notice in this case, instead of 2, we have these 3 here, right? Because we did this mod 3, or mod 1 minus omega. Let me see what else. Oh my gosh, I guess that's it. So let me end before I end here. Right, so what did we do? We looked at the Collatz problem, then we looked at the Collatz problem over the Gaussian integers, and then we tried to look at the Collatz problem over the Eisenstein integers, and there's still a whole lot of work to do. I thought I had another slide here, but maybe I didn't. There's still quite a bit of work that can be done But what we at least finally, eventually did recently was we did finally get these results submitted to the Minnesota Journal of Undergraduate Mathematics. So hopefully this will come out soon. I'm not sure how long this usually takes, but that's where we're at with this particular problem. Future directions, what else do we want to do? I've mentioned a few along the way. Continue investigating the Collatz problem, maybe over other lattices, or even just stick into the Eisenstein and Gaussian, and what else can you extend any of the work that's already been done. But I end with this quote from Tao. I don't remember if this was from this article that he had that was in this Quanta paper, or maybe this was from his talk. He's got some really nice slides if you search online. But he says you can get as close as you want to the Collatz conjecture, but it's still out of reach. Either way, it's still a fun problem. So if you want to talk more about it, I'm happy to do so. So with that, I'll end. Thank you.
So I noticed for your Collatz maps, so for the modified one over the integers of join I, you used two cases in the Collatz map. And then when you went to the Eisenstein integers, you used three cases.
Yeah.
And those lattices correspond to, so in the first one, you're joining the root of a degree 2 polynomial.
Yes.
Next one, you're joining the root of degree 3.
Yes.
So I guess my question is, would you expect over an integer lattice where you would join a root of a degree n polynomial, would you need n cases in the modified Collatz?
I think that's what it was looking like. Yeah, I would think so. But can we make the same sort of statement where we expect it to reach a unit? I don't know, because in both of these cases, well, in one of them, it looked like, just by experimental results, it looked like maybe not, and then in the other case, it looked like maybe it would. But yeah, no, I agree. You're right. Yeah. Did you?
So for you mentioned about the order of the number of moves it takes to get to a unit from a starting number. So do you have any information for integers or Eisenstein numbers on the current upper bound for all of this? Because I don't know.
Yeah. No, that's a good question. So upper bound. So we didn't get to spend enough time on the Eisenstein integers like we did with the Gaussian. But what's a possible upper bound? I don't know, but I think that's a great question to ask.
Yeah, because I remember you said that 27 would take over 100. So that was pretty interesting.
Yeah, that was for the rational.
For the integer.
Yeah, and I'm sure there's there's definitely better results online for the Gauss, for the regular Collatz problem. I just don't remember. Yeah, I don't remember what the highest value is, but we do at least have this one here. So this one goes all the way to 100,000, but I'm sure, but I mean, we picked a number 2 to the 68. So, or at least those values have been checked up to 2 to the 68 that they will eventually reach 1. So 2 to the 68 divided by 2, right? So definitely that's a bound right there.
So how do we make the problem harder?
How do we make this harder?
How does this been made harder? This problem is harder. Do you expect them to pattern to over to solve the original problem?
I don't see how, say, for example, looking at the Collatz over the Gaussian or Eisenstein, I don't see that it could help with solving the original conjecture. but it's still such an interesting problem to look at it. Yeah, we didn't bother to try to solve anything anywhere for the original Collatz, because I just knew we weren't going to get anywhere. So that's why I thought, well, maybe we could get some results by looking at this over the Gaussian integers instead of the regular integers. So, yeah. The fact that it contains this root, so like omega and I, yeah. I haven't thought of it that way to see if that, yeah, we didn't get enough time to look at the Eisenstein, for example. We didn't get enough time to look at that, but that would be interesting.
So on the Gaussian, when the Gaussian converge, there was like an
how far did we get? Oh, I think the page with, yeah, 251 was the slowest. So, but that was only checking a few. That was only checking this area close to the origin.
Yeah,
I don't remember. I'd have to go back and check, but but I know that we wanted to look at the same questions. We had the same questions, but I don't think we got very far with it. Yeah.
We go to finding the evolution tree for the Eisenstein. Yeah, that. So I see that all worksheets either have invariant 1 or 3. There were 2. Did you engineer to never have 2, or did that emerge?
No, this is just how it came out. And I imagine because of the way it's defined, where we have these 3 congruence classes, I imagine that's why, but that was exactly what they had noticed, is that there's either only going to be 1 or these 3 branches, but we didn't have anything with 2. Yeah.
Do you know that's true in general? Or
I don't know in general if that's true, but for this example, it makes sense that it would be 3, but we didn't prove it. We haven't proved it. Okay.
How do you charge the probability value of Gaussian integers to Eisenstein?
The probability method?
Yes.
So yeah, so what they did was they basically, so let me see. They tried, yeah, they did do a little bit with that. That's where they came up with, where was it? Let me see. Yeah, so they tried it here. So if they follow this argument by Crandall and try to make the analogy with the Eisenstein, for example, it looks like that it would eventually reach 1. They came up with the PDF, right? You have 3 choices. So either one of these will be, let's see, how do I call it? Even, odd, and I don't know what to call this third one, right? So let's just say if it's odd, we stop, and if it's not, then we keep going. Then you have these other 2. And then you apply the Eisenstein again, and you have to check these 2. Okay, is it even, odd, or something else? And if it's odd, you stop. If not, you keep going. And they did try this argument that can be found in his paper. They did try this for the Collatz function over the Eisenstein as well as over the Gaussian. And they came up, they found these two different values, or these two different results in what appears that for the Eisenstein, it looks like it will eventually reach 1, but for the Gaussian, it did not. And at least from the preliminary results, from the values that they looked at, it looked like they just kept going. If you took their norm, it looked like it just kept getting larger and larger, only for a small number of values that we looked at. I think they did for the Eisenstein. I think they did. I think that was.
There are no numbers that we know. I mean, all the numbers didn't show either.
I'm embarrassed to say I don't remember. So let me see, what did this picture? So these were the trajectories. So these are the trajectories up to length 24 using U as 1 or minus 1. And I think if there were any blank spots, then that means we didn't have any results, or it just kept going too far. Yeah, I don't remember, but I'm going to have to be better prepared next time.